Good afternoon, everyone. My name is Jianyu Yin. It's my honor to be here presenting on the topic of bridging the annotation gap, innovating through defects detection with weakly supervised object localization. I'm a third-year undergraduate student currently pursuing my bachelor's degree at the University of Macau, and I have been working under the supervision of Dr. Xianfei Yin. So why do we care about sewer systems? Sewer systems are critical infrastructure that, if not properly maintained, will pose risks to public health, disrupt people's daily activities, and pollute the environment. Currently, sewer inspection involves collecting CCTV footage, which is manually inspected by professionals or aided by computer algorithm. Among those, deep learning-based detection models have been increasingly used due to its superior performance. However, traditional deep learning-based defect detection models rely on detailed feature-level annotation, and creating these bounding books is very tedious. To address this gap, we explore the method of weakly supervised learning using class activation map. CAM is a technique that generates a heat map to highlight the most important regions influencing the model's classification decision. But as you may notice, the model is actually trained to classify the object well, but not to localize the object well. Such gap between classification and localization leads to the original CAM methods tends to focus on only the most discriminative feature of the object. So but in sewer systems, the full shape and scope of defects are crucial for remedial actions. So in this study, we adopt an advanced weakly supervised object localization algorithm that introduces those functions tailored to address this gap. For example, for defect of root, this is a heat map generated by the original CLM method, and this is a heat map generated by our advanced CLM methods. The dataset utilized in this research is SewerML, which is the first publicly available dataset for sewer defect classification. So it only contains image-level annotations. To meet the WSOL test requirement, only images that have one class of object were chosen. We evaluate our approach using both ResNet-50 and VGG-16 backbones. The models were pre-trained for better initialization. So these are some localization results. For example, let's look at one image. Oh, sorry. Yeah. So let's look at one image. For example, for a defect of cracks, this is a heat map generated by the ResNet-50 models. And after we apply a thresholding value, the predict bounding books can be drawn on the original image, which is the green bounding books. And the blue bounding books represent the ground truth bounding books. The closer the two books are, the better the localization precision is. We use confusion. Collapse and RB cracks. We believe that the model's classification performance can be improved if they were separated during training. One important factor we investigate was the effect of thresholding. Thresholding is used for drawing the bounding books up from the heat map. Simply speaking, we set a threshold value that any pixel value higher than the threshold value will be considered as object, and lower than the threshold value will be considered as background. But the question is, do we set a fixed threshold value for all the images, or do we apply different threshold value for each defect classes due to each class's unique characteristics? This is a localization accuracy varying with the threshold value. We can see that the ResNet-50 models reaches its maximum localization precision at a threshold value of 0.07. But if we apply this threshold value for PB class, its localization accuracy will drop to nearly half of its maximum localization precision. Thereby, we suggest using different threshold values for each defect classes to optimize the localization precision. We also studied the effect of training set size. Generally, more data fitting into the model, the better the localization precision is. But in WSOL task, we can trade classification accuracy for better localization accuracy. And only when the training set is too small, for example, less than 100 images per class, will there be a huge drop in the localization precision. Finally, we studied the effect of validation set size. Well, in deep learning, validation set is used for hyperparameter tuning and model selection. So bounding box annotations are inevitable to compute the localization performance. This is different from the training set that only use image-level annotations. And the more bounding books used in the validation set, the better the localization precision. So it's important for future researchers to fix this number of the samples in the validation set, as we need to know any improvements in the model are genuine or they are due to unintentional use of more bounding books in the validation set. Our future research directions include transition from WSOL to WSOD to enabling multiple defect detection at a time. Also, we will benchmark in different WSOL methods, including language models and different backbones for the same WSOL model. Our ultimate goal is to develop a completely automatic search systems. Our work has eliminated the need for bounding box annotations for developing an efficient defect identification system. But we will further investigate such as using unsupervised learning techniques for using raw images to get the classification results, and ultimately input raw images to get the detection results. Thank you for listening.